Weathering descriptions and zonations. To formally start, weathering is a graduational feature, and to deal with such features, the usual approach is to impose boundary conditions within them so that they are divided into various grades defined by a range of characteristics. This depends upon two factors. First is the change in engineering properties of the rock material, and second is the volumetric regularity or irregularity of this reduction within the rock mass. So, as we all know, weathering is a very broad topic. So, in here, it describes that weathering is a gradational feature. So, in layman's term, gradational is what do you call a step-by-step process. So, so now we use methods to divide weathering to specific characteristics or grades. So in doing this, we need to keep in mind that there are two factors in for us to divide the weathering grade. This is the volumetric regularity or irregularity of the rock mass and the engineering properties of the rock material. The first part in imposing boundary conditions is the use of the basic types of mass weathering, namely uniform weathering, complex weathering, core stone weathering, and solution weathering. So, by definition, uniform weathering is a gradual decrease of weathering grade and intensity with depth in thick strata of homogeneous lithology. So, to be simple, weathering is uniform weathering is the weathering of a certain part of land that has uniform weathered characteristics or the same characteristics of weathering in a place. So the next is complex weathering, which means an irregular weathering profile in layered lithologies that have different susceptibilities to weathering. So complex weathering is uh, as as stated in its meaning, it is an irregular pattern wherein different characteristics are found in the area of the layered lithologies. So next is the core stone weathering, which is mostly coarser grained igneous rocks. Rounded core stones of almost fresh rock may be surrounded by very decomposed, highly friable material, similar to a compact sand. Here, the core stone weathering is very simple to understand. Suppose there is an large piece of rock in an area, then it is surrounded by what do you call this pulverized soil. So as time passes by, weathering happens, thus resulting to the the large rock becoming much larger because the other pulverized soil combines, which is why making it more which is why making the large rock larger. Uh, so next is the solution weathering, wherein it means carbonate and most salt rocks weather by dissolution. Joints and bedding planes become open and underground caverns may develop. So So solution weathering is a weathering mainly caused by chemical reactions. So as we all know, salt combined in soil can easily dissolve through weathering such as raining. So in 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 instances like caves, high salt concentration in the soil can lead to many chemical reactions. Then let's proceed to the next topic. Next is the observed weathering significance of mass weathering. First is effectively unweathered. Second, significantly weathered. Third, severely weathered. And fourth is the residual soil. So, to give you an overview, it is how the rock materials it is how weathering have affected rock materials to a certain degree. So first is the effectively unweathered, which is the weathering of rock mass that any engineering work may be constructed or on or without regard to the weathered condition as found. So kini kay effectively unweathered, meaning that any engineering project can still continue in spite of the weathering that it experienced. Kanang pwede ra nimo baliwalaon ba kay dili mura mag close to wala ang yang epekto sa material. The next is significantly weathered. The weathering of the rock mass is such that some regard must be taken of the weathered condition of the rock mass in the design and construction of some particular engineering work. So, as per definition, murag kailangan ka magbuhat o kanang measures para makuan ang katong ginagmay lang siya nga ang severely weathered kay ay significantly weathered kay kailangan lang ka magbuhat og mga precautions gamay ba para ang katong imuhang material kay dili kay siya maapektuhan kay gamay ra ang epekto sa iya ba. So next is the severely weathered. This means the weathering of the rock mass is such that the weathered condition of the mass dominates the design and construction of any engineering work to be constructed on or in it. So, severely weathered. This is the one of the critical effects of weathering because the part of the rock material is affected by weathering. Kanang ang yang durability, ang iyang design nadaot to ba kanang murag halos 75% sa iyang aspect na daot, meaning kailangan juga murag the weathering dominates ba kanang na makita gini mo mga murag na daot yun siya. So last is the residual soil, which is the sufficient of the rock material is decayed to the geotechnical condition of a soil to make the mass behave as a mass of soil. It may be important because of their influence on, for example, slope stability, to distinguish between those residual soils that are structureless and those that have relic discontinuities. So residual soil is kanang mga ang kanang base form sa kanang murag core property sa rock mass ba kay murag na daot na god, murag na decay na kay tungod sa kadugay or sa kagrabe nga na apekto sa weathering sa iya kanang dili na siya magamit ba kanang silalom morning main cause that is why engineers effectively study the slope stability kay ang sa ilalom mao nang kuan kanang iyang strength property kay dili na kayo makadaog. So for example kay diri sa slope stability, slope stability, relic discontinuities kanang musta sa mga kuana siya sa ilalom. Then that's all para sa kanya topic. Next is the three main conditions of the discontinuity weathering. So first is the fresh. Next is surface stained. Lastly is the surface weathered. So fresh is there is no sign of weathering found on the material, or in other words, the material is unaffected by weathering. Next is the surface stained, wherein there is no or little penetration of weathering into the wall rock, so that the discontinuity asperities have the strength of fresh rock. So here is surface stained, or in vernacular is what you call kanang gamay-gamay lang maragpasa lang gamay sa rock material. So diri kay nagmean nga there is little or no wala kayo naka-apekto ang weathering sa rock discontinuity. Next is surface weathered, wherein weathering penetrates to a depth greater than the roughness or undulations of the discontinuity surface. Here ang kini kay kuan ang weathering nakasulod sa ilalom sa discontinuity surface, kanang naka-apekto gid siya yang performance ba sa yang strength sa sulod. So next is the three main conditions of rock material. This is the same as the three conditions of discontinuity weathering. It's just that the names are somewhat changed. So first is the fresh condition, second is stained, and lastly is decayed. So first is the fresh condition, wherein there is no sign of weathering. Just like the conditions of discontinuity weathering, there is also a fresh condition of rock materials, wherein there is no sign of weathering to the rock material, meaning that it is unaffected by weathering. Second is the stained condition, wherein the material is weathered but without obvious loss in strength. So ang kini kay ang rock material kay ning makita gyud nimo siya nga na-apekto siya sa weathering, pero ang iyang strength walay kanang durable lang gyapon siya, or fresh lang gyapon yung condition, pero gamay murag niagi lang siya weathering gamay. As the definition says, without obvious loss in strength, so that you can understand it by the meaning. Next is the decayed condition, wherein deeply stained and with obvious loss of strength, perhaps friable. So friable means kanang gabok in Bisaya, or kanang hapit na gud siya gamay lang nimo nga anak nga tandog muna na siya maliki, or ma-pulverize kanang hapit na ma-pulverize ba kanang gabok. Then this happens because the rock material experiences severe weathering, kanang grabe na nga weathering ba. Tapos ang kini syempre weathering tigulang na, meaning gabok ng iyang structure sa alam, iyang strength gamay lang strength. That's all. Next is the ground mass description. Most cases of ground volume is always investigated and described with the aid of core recovered from drilled boreholes. Then the borehole core provides a description of the vertical profile, but at some stage, a general description of the volume is needed. This means that ground mass description is often observed because you can see the soil itself, but it needs thorough investigation for you to conclude the stability and strength of the said area. That is why you use cores excavated from drills or drilled boreholes. Next is the general mass description. Most ground masses used in engineering works are considered to be composed of a series of geotechnical units which are distinguished by a particular mass properties. The range of properties defining a unit is assigned by the investigator, commonly with regard to the particular type of engineering work to be performed. Uh, for us to understand its meaning, let's just use an example to clarify things. So, suppose there is an area wherein we excavate it to form a large road cutting. Then it then the area excavated divided is divided into several parts in order to make things easier. Then in order for things to be easier, the excavated parts are used in different purposes, such as water bank, uh, embankment fill, and with regards to slope stability. Uh, mm, Also, just imagine that not all not all materials is not all materials is excavated is used for that same engineering work, but can be also used in other parts of engineering. Core logging. In order to identify what is core logging, we must know the meaning of a core. So, a core is a mineral derived from the soil through drilling. Then, core logging is the systematic recording and measuring of information to determine the lithology, mineralogy, potential geological history, structure, and alteration zones through a tiny piece of cylindrical rock drilled and removed from a potential mineral deposit. And this means that the cores driven by drilled boreholes from mineral deposits are examined and measured to describe the said area, to describe its geology, uh, lithology, and potential geological history. Next is poor or inappropriate core logging can lead to major civil engineering claims. Accordingly, accurate core logging is one of the most important activities for the engineering geologist. So, like any other jobs, uh, core logging is um wait lang guys. It is an important activity because it needs proper procedures in order for it to be successful. Next is course taken as part of site investigation for an engineering project should be logged by an engineering geologist rather than a geologist itself. The content and emphasis of the descriptions will depend on the recognition of the importance of geological factors revealed in the course of the particular engineering project. This means that the course excavated from drills should be managed by an engineering geologist. Let us replace it, engineering geologist, meaning engineer that focused on geology, because he is the one who knows the process of core logging. But if the course that have been studied is very very intrinsic, that is the time we should call a geologist. So these are the examples of the cores being logged, wherein they are being put in a different boxes for them to be analyzed. Next is the basic requirements for good core logging. It is that the contractor and the consultant must ensure that the cores are placed in good condition, well labeled core boxes, and are stored so that their conditions are recovered from the borehole is maintained. These cores should not be allowed to dry out, be eroded by rain, or frozen. This is just proper procedures in any work. But for cores are very fragile, which is why it needs strict procedures for it to be maintained. That is why you should refrain it from being washed being washed by rain. Dili siya mainitan, o di po siya dapat makuhanan sa kanang ma-ice or frozen. Next is the process of core logging. Ideally, all the cores should be logged in one exercise, and the logger must be fully aware of and understand the nature of the engineering work, so that the log gives the information necessary for the design of the work. So, obviously, the logger should be familiar and well informed about the course being studied. So, I will show you the steps of core logging. First is that the cores should be logged as they come out of the borehole, for their description may influence the further development of the investigation. Right after being excavated from the borehole, the cores should be investigated at that moment, because it may change as it is being stored. Next is that for the final log, the logger must look at all the soils and rocks to decide provisionally what they should be called and in what detail they should be described. A published system of description should be used and its selection justified. So obviously, the final list should be based on the characteristics of the soils and rocks that the cores are drilled out. Lastly, the final step is that the cores should be sorted out, that they fit together as well as possible to allow total core recovery, and if required, solid core recovery, and rock quality designation. This means that the last part is that the cores should be sorted out in each varying characteristics. and it falls into three main categories. The cores are sorted out in three different categories, namely the total core recovery, next is solid core recovery, and lastly is the rock quality designation. Um, First is the total core recovery. The core is sorted through its length divided by the length of the hole drilled. That is just self-explanatory. Next is the solid core recovery, wherein the total length of the solid core cylinders as a percentage of the core run. Um, total total length of solid core cylinders is the cylinder wherein the box wherein the cores are being placed over the core run. Next is the rock quality designation. Total length of core sticks longer than 4 inches expressed as a percentage of the core run. This process is somewhat being disregarded by many engineering geologists because of its inaccurate not inaccurate but irrelevant results. But for information, but for extra information, this is the total length of core sticks wherein it is mainly in at the size of 100 millimeters. Then it's divided into by it is divided by the core run. The next topic is recording. Recording is the logging process which is accompanied by doing discontinuity measurements first, as this process gives another chance to look at the rocks and consider the descriptions to be used. It also features the cores resulting from drilling, which have to be identified. Thus, ends of core runs tend to be more broken, while core springs may produce scratch marks, simulating bedding. This means that recording is centralized in two factors, wherein the logger should describe the materials that have been excavated and describe the discontinuities of the materials. Next is the discontinuity orientation. The depth of discontinuities may readily be measured on cores from a vertical borehole. However, the direction of depth can only be measured with special and usually expensive equipment. If the direction of depth of the dominant integral discontinuity is known, it is possible to measure the direction of depth of other discontinuities relative to it. This is just the procedure in determining the discontinuities of a said material, wherein you use expensive equipments like the dip. Next is the daily logging rate. A good core logger giving a full engineering geological description for a complex project can usually manage to log about 30 meters of core a day before the mental indigestion sets in. It is much better to do the work in a well-lit, air-conditioned hut, sitting in a comfortable chair with a pot of coffee at hand. And like any other work, core logging is very tiring. So, for example, imagine doing a core logging in a very dirty swamp wherein there are many mosquitoes around. unlike to doing work in a well-lit, air-conditioned hut and sitting in a comfortable chair with a pot of coffee at hand. This means that in order for the engineer to log the core excellently, one should be comfortable with its working environment. Our next topic is about a theoretical example of the drilled cores. So, on the right side, you can see an illustration to visualize the points of the topic. So, first, there are 3 core boxes. Look closely because you can see 3 core boxes being contained by a rotary core drilling from 150 to 38 meters depth or 15 to 30 meters drilled below ground. So, the upper boxes contain 160 millimeters diameter core, while the lowest is containing a diameter core of 120 millimeters. Also, the drillers has marked the beginning and end of each core run. Second is that the cores have been placed in the core boxes to more or less fill them without breaking the cores more than is necessary. But there will be some fitting breaks, and one of the first tasks in logging is to identify them. One such is to be found at point A. Look at the second box, point A. They would not be counted as natural discontinuities for RQD measurements. So, in logging, the first step is always observing the breaks in the course. Third is that the course on the first box shows a fining upward succession of rocks, which is the conglomerate to sandstone to sandy mudstone, then mudstone, and lastly coal. The fourth is the rocks at sea, just below the 18.75 meters core run marker, are rather broken and may represent an over-drilled core stub. As you can see, the rocks at letter C, that is in the first box, the third layer, wherein you can see the broken parts. Fifth is that the fragments of rock at D would not appear to be in the correct place and may come from the bottom of the run at 22.5 meters. Gets? Sixth is that the joint at E may be open, and if when its two surfaces are placed in contact, the thickness of the core is less than the diameter drilled, then the joint is open and the aperture can be calculated. Lastly, at F, the core is very broken, and at this point, the driller decided to reduce core diameter, presumably as a result of encountering drilling difficulties. Such difficulties would be recorded in the daily drilling log. The implication is that the breaks in the core above and below 31.05 meters are a consequence of a natural phenomena and not the drilling itself. The same remark could apply to the broken core just above 38.06 meters. But here, it might also be the core cracking in the vicinity of the core spring on breaking off of the core to pull it to the surface. Next is the describing of lithologies. From the illustration given, you can see that there is a clear difference between the strata above, about 22.7 meters, from 22.7 meters to 31 meters and below this last depth. In the case of strata above 22.7 meters, there would appear to be a cyclic deposition in fining up sequences. Sorry for that. And at about 22.75 meters, a conglomerate is found composed of limestone, pebbles, and may well mark in unconformity. Also, a check on the relative ages of the limestone and overlying cyclic deposits would be of value for the unconformity surface, wherein that it is very irregularly eroded landscape. Lastly, below about 30.9 meters are the mudstones and sandstone, are again encountered although lacking indications of cyclic depositions. However, while their bedding below 32 meters is regular and thin between 31 and 32 meters, it becomes variable with indications of folding. This can be sedimentary, but is probably faulting. Lastly is the strength and structure of the materials, wherein their strength is assessed by an equitip rebound number or some other methods, but indicated in the log by the terms used in the scale of strength for rocks. Example, moderately strong. This means that the rocks are examined thoroughly through core loggings and is described by their strength factors.